Thank you. Yes, I'm continuing on the story of stellar streams, but now moving beyond our own galaxy. So just a quick recap. There was actually a very nice review paper on stellar streams last week by Anna and Adrian, which summarized the status of streams in the Milky Way right now after Gaia. So we have more than 120 reported stellar streams in the Milky Way, and the word reported here is important because not all of them have been followed up yet with kinematics. So we're still discussing a bit in the field how to actually define when something is a stream. But here you're seeing Gaia data in log density, and overplotted are all the footprints of known streams and their widths and lengths. So the wider streams are typically these dwarf galaxy streams that are dynamically hotter, and the thinner ones are the globular cluster streams, which we've heard are very useful for the dark matter subhalo searches. So we've heard versions of this already, but different prescriptions of the nature of the dark matter particle predict different types of both clumpings and distributions of dark matter in galaxies. So here you're seeing CDM versus warm dark matter, and what you can pick out by eye already is this difference in subhalo distributions. And we've heard from the very first talk of the conference by Lynn that stellar streams are actually sensitive to this 10 to the 6 solar mass subhalo, so we're in this regime where you actually can differentiate between the different dark matter predictions. Something we've talked a little bit less about in terms of streams is that they're actually also sensitive to the halo shapes, and this is just me painting in Keynote, so don't take this too literally. But stellar streams have actually been used in our Milky Way to get at the local acceleration field and thereby the mass distribution of dark matter in the halo. And we've done this in the field using individual streams, but now also moved towards Anna Bonatz's paper here from 2018 with David Hogg, where they actually use joint constraints from multiple streams and show that different types of streams located in different regions of the halos constrain the local acceleration field. Let's see. Okay, so I want to make the case that we should try to go beyond one galaxy. So we've heard about this a little bit today in Karlberg's discussion section after his talk, but there are other things in the Milky Way that can actually lead to gaps, and that creates a problem for us. So in 2017, I had a paper showing that these thin globular cluster streams, here Palomar 5 projected onto a Milky Way-like illustration, could actually also have gaps induced in the streams by interactions with this central stellar bar that we believe the Milky Way actually has. So the bar are these elongated rigid structures moving on different orbits with respect to the disk, so they're rapidly rotating and can actually also lead to gaps forming in the streams. So what happens is that even though your stream is not orbiting in the plane of the galaxy, it could have come in with an angle, it still experiences a net torque, and depending on where you are in the stream with respect to the phase of the bar, meaning if you're ahead of it or behind the stream, you either get a positive or negative torque. And in this system, your Jacobi energy in the co-rotating frame is conserved, which means that a shift in your, or a torque from the bar leads to a shift in the angular momentum of the stars in the stream, which then in turn leads to a shift in the energy. And we know that streams are actually elongated structures because these differences in their energies compared to the progenitor system. So actually this leads to gaps forming. And this is now not showing up super well, but it's just an animation of a Palomar 5-like stream that actually then is on somewhat of a polar orbit, but still as it reaches pericenter, will feel this perturbation from the bar, and that's time dependent and also depends on for how long you're interacting. So things like the angle of your orbit, the mass of the bar come into this calculation. So there are also other things that can do this, molecular clouds, spiral arms, and Ray alluded to the fact that at least this is confined to when you are close to the disk. So I do want to say on a positive note that in the Milky Way, is again from Anna's review from last week, blue streams here, or bluish colors, are showing retrograde streams. So streams that are not moving in this co-moving with the disk actually are less susceptible to these perturbations because they interact for a shorter time. It's more of an impulsive kick. So there is hope that we can still use some of the streams in the Milky Way. But I will here argue that if we can actually go beyond the Milky Way and target galaxies that don't have galactic bars, or target streams that are further out in the halo, which would be easier to detect extragalactically with respect to the backgrounds of the stellar halos, we can maybe get to some interesting results. Then there's the dark matter halo properties. If we actually want to use streams to get at the shape of the dark matter halo, it would be really nice if we move towards comparisons between what our predictions for what are measurements for many different dark matter halos, not just the Milky Way, and also have rigorous ways of comparing that to expectations of shapes and mass distributions for different dark matter prescriptions. All right, so the problem is that we've actually only so far observed stellar streams from thin globular clusters in the Milky Way. We've never seen them extragalactically. And we have seen many of these dwarf galaxy streams extragalactically, but not a lot of them have been used for dark matter science yet. It's more been used as kind of a demonstration on how hierarchical galaxy formation is real. So we're entering this really exciting era where a lot of stellar streams will be observed in the Milky Way. So these are both planned and ongoing missions already. And with these, we'll actually get thousands of stellar streams out to maybe 100 megaparsecs. And I'll elaborate on that a little bit. But there are things we need to tackle before we can actually make use of these streams. First of all, we won't have kinematics. And we've heard in many of the stream talks so far how kinematics really seem to be key to get at the dark matter halo masses, so that's subhalo masses, so that's kind of a problem. You're now seeing your data in projection, so it's a different geometrical problem. You also have the viewing angles of the galaxies. And then we have poor data quality overall. So there are things we need to tackle before we can use these extragalactic streams. And I have now spent the last 5 years or so thinking about this problem and how we might best be able to move forward and do dark matter science with these stellar streams. So the Roman Space Telescope is exciting. It's a planned NASA mission, and it's exciting because it has 100 times the field of view of the Hubble Space Telescope, yet the same resolution. So this means you can really get at these stellar stream-like features that extend over large areas on the sky. Before Gaia, the way we actually searched for streams was mostly through something called match filtering. So here you're seeing not Palomar 5 yet, that's actually a different cluster, but you're seeing position on your left, and then on your right, you're seeing a color magnitude diagram. So the colors of all those stars in that field, and then this turquoise line is an isochrone, and that whole idea with match filtering is that when you're looking for streams, you're looking for typically old globular cluster type systems, and in the case of Pal 5, you actually know the metallicity and mass of your cluster. So that helps in terms of how you search for these. So what you can do is you can step forward and backwards in distance modulus and see at some point right now, your stream pops up at about 20 kpc. You can also see there's a distant gradient along the stream. And this is actually how we've been finding streams for most of the time that people have studied stellar streams. So it's by squinting at these maps where we didn't need kinematics. So Gaia has, of course, changed that in the Milky Way, but extragalactically we'll need to play a similar game still. So I took Palomar 5 and just looked at what part of the color magnitude diagram do we actually see of the isochrone in the Milky Way current data, and you got way below this main sequence turnoff, which means that you have a lot of stars to work with. We then tried asking, what if you take something like Pal 5 and inject it to Andromeda? So we saw this in Asi's talk yesterday, a version of the PANDAS data, which is a very nice field of M31. It's not showing up super well here, but you can actually see dwarf galaxy streams already. And then we asked, would we be able to find something like Pal 5 in this data if we injected it with current limiting magnitudes? So we find that we are sensitive to something like 5 times Pal 5 in the PANDAS data, but that we wouldn't be able to find an actual Pal 5-like stream yet in current data. And then the exciting part is that with Roman, a 1-hour Roman exposure, you actually get below this main sequence turnoff, and you could easily find these streams, and even down to 50% of Pal 5's mass. So just a little bit more details on how we did this. We take a Pal 5-like stream, inject it into mock simulated data of what Roman would look like in Andromeda, and then I developed this Huff stream spotter code to extragalactically determine whether or not you found a stream or not. And this is again playing a game of what's your signal with respect to your background. And it might surprise some people that the field of automating stream finding is actually very new and growing over the last couple of years. But what we do here is we take each position of all the stars here on your upper left. We do a Huff transform, which means that you're then moving from one point into each point having a full sinusoidal curve. And the way you can think about rho and theta is that rho is almost an impact parameter. Here on the left, you're seeing a fixed rho, but different angles. And you can see you're kind of mapping out a distance from the center of your field. On your right, you're just seeing fixed angle, different rho, and you can see you find then what angle your stream is at. The powerful idea in this is then you can do an inverse Hopf transform on this rho theta space and very easily recover a stream. So we did this in mock Roman data for the Andromeda Galaxy. We also did it on current pandas data in the Andromeda Galaxy, and that's how we then set these limits on what's detectable with Roman and in current data. So I think this is exciting because this opens up a whole new field of other systems where we can study gaps and also just find these thin globular cluster streams. And this all depends, the exact limits depends on a bit of what type of cluster stream you're looking for. So Christian Aganse, who is now a fellow at Stanford, he then took this a bit further and said, what if we simulate a interaction with a dark matter subhalo and take one of these streams and ask what happens if we move that to extragalactic systems? Through that, he found now you're looking at, again, simulated Roman data, but now with distance to the galaxy of interest. So you're seeing moving down in distance as you're moving down in the panels. Then we applied something called find the gap to, again, do this more vigorously than by eye, but where we can actually automate the detection of whether or not we see the gap or not. And Christian found that out to about 2 to 3 megaparsecs, you can find these gaps in streams. So that, again, opens up a whole new era of doing this gap statistics in way more systems. And we can get into all the problems that also arise from being extragalactic. So I think that's already exciting. There will be a whole other galaxy like our own Milky Way where we can do this and look at the subhalo mass function. So there's a sweet spot, and we heard about this a little bit from Ray already, that you want to be far enough from the galactic center that you're not necessarily perturbed. You won't necessarily know this exactly because you don't know the full orbit, but far enough from the galactic center that you can be detected and also not are interacting with these baryonic perturbers at the centers. And then, of course, you've got to be close enough to the center of your galaxy that you can still tidally strip. So Anna and I addressed this in a paper that was on the archive last week for a slightly different reason. We tried to figure out how many streams there might be missing in the Milky Way. And here you're looking at the footprint of the observed streams in the Milky Way that are known so far beyond 15 kpc. So there are a few, but they're actually not that many, especially not if you make the cut at 30 kpc, for example. So Anna and I used catalogs from Chen and Gnedin that trace globular cluster formation through a hierarchical model where you take merger tree information from TNG galaxies, and then you actually have a post-processing step of triggering globular cluster formation, and in their catalogs, they actually trace all the way down to tidal stripping and have the information of what streams are doing. So Anna and I looked at that, and we found that there's actually 10,000 fully disrupted objects in the Milky Way, in a Milky Way type galaxy, and that at present day, about 1,000 streams should be surviving. So that's a lot more than the 100-ish streams we've found. So I think that's exciting, both in terms of there's still more to be discovered in the Milky Way. And then what I'm interested in, though, is that the ones that are located far from the galactic center actually seem to all be from accreted streams. So this again tells us something about where we should be looking and focusing our survey. So there are a lot of subhalos in the outskirts we've heard, and luckily there are streams that we'll be able to find in these outskirts. Caveat in Milky Way type galaxies, and we can get into that a bit more. So again, just comparing to what we've seen for fully disrupted clusters in the Milky Way, there's a huge potential population of streams that we can detect. Okay, so this is just saying in the Milky Way, there's a lot more to be found. Okay, so to sum up this part of the talk, I've now shown that we can get at statistical samples of gaps in streams, but of course there are all these open questions of how do we know if it's actually from a subhalo, how do we trace back the mass of that subhalo, and that's something I think we should all discuss. But my point here is that maybe with statistical samples, you could marginalize over some of these effects if you know the rates. Robin was talking about that in her talk earlier yesterday of the rates of subhalos. You could maybe also have rates of how likely is it that you interact with a black hole in the halo, or how likely is it that a globular cluster hits you and perturbs you. So that's some way of getting around that. Okay, so in my last 5 minutes or so, I want to move to the dwarf galaxy streams, which all of these different surveys will actually be able to find. So there are cases in the literature where stellar streams around extragalactic systems have been modeled, and you can do this very successfully. Here's an example from Van Dokkum and Bonazza from 2019. However, not a lot of work has been done on actually constraining dark matter or constraining the distribution of dark matter around galaxies from this type of work. The reason for that is that it's a hard problem. So if you imagine this as a projection on the sky of two extragalactic streams, here on your left, you're seeing a stream devolved in a very high mass dark matter halo potential. On your right, you're seeing that in a lower mass dark matter halo potential. So this is bad, right? These two streams look identical, and they even have, so they have this degeneracy between their morphology and the halo mass. By just looking at the morphology, you actually have no idea that one was in a more massive dark matter halo. So that's not great if we want to actually use this to learn about the dark matter halos. These have the exact same orbital properties in the sense that they have the same pericenter and apocenter, but they've been evolved, integrated for a different amount of time to get at the same length, and I'll get back to that. So what's going on here? How can we actually have two streams that look so similar? What's happening is that in these two simulations, one has a much lower mass, or half the lower mass progenitor, or sorry, not exactly half, a fourth. And that is in order to get the same tidal radius, right? So to get a morphology that looks identical, you need to have stripping at the same type of tidal radius. So to do that in the right case, where you have a more massive host, or less massive host, you need to also scale down the progenitor. So this is one difference we could go out and look for. But one that makes this really hard is often we don't really see the progenitor. Second thing that makes this hard is that it's actually really hard to get at the stellar masses observationally. However, in order to also reproduce the exact same orbital nature, what's actually happening in this case is that the velocity along the stream, so this is now line of sight velocity, which we can technically observe, is very different. And it's a deeper argument than the stream would just be unbound if it was moving a lot faster in the right case, in a lower potential, but it's actually to reproduce that morphology of the stream, you need to also scale your orbit accordingly. So this is exciting. There's actually hope to measure these differences in the radial velocities, and that breaks the degeneracy. So if you can measure a radial velocity, you can break this halo mass stream morphology degeneracy, and also the velocities along the stream are informative, and those are harder to get at observationally, but not impossible. Okay, so in a paper a few years ago, we looked at the Centaurus A galaxy, which is about 4 megaparsecs away, and saw that they have this beautiful stream data around its stellar halo. And interestingly, there's actually a nuclear star cluster at the very center of this stream, so it's one of those cases that has a progenitor with a radial velocity measurement. So we used that to then play this game of how massive does your halo need to be in order to still be able to reproduce this stream with that radial velocity. And then you can step down and see that at a certain case, this whole thing breaks down. At a certain mass, you simply can't reproduce the morphology of the stream given that radial velocity measurement. So this is early days, of course, so to get from this a mass lower limit on the mass is exciting. We can learn something from the streams in extragalactic systems, but to back out then what is the complete shape of the halo is, of course, a much harder problem, and also to compare that to expectations from dark matter is a much bigger task. But I will say, excitingly, Jake, Neibauer, and Bonazza last year had a paper that showed even just the morphology has information about the shape of the halo, not the enclosed mass, but actually the shape of the halo. And I hope Anna and we can also discuss that more later. But I think this is exciting for the field, right? So we're not there yet where we can use streams to measure differences completely in the shapes of the halos, but I think because we'll have 1,000 or more than thousands of these from the upcoming surveys that it's important to think along these lines. So with that, I'll leave my summary and just say that one of the biggest things needed now, which is what I'm working on with my new group in Copenhagen, is to really do these vigorous comparisons between what we learn from the stream data and what dark matter predicts. So that's why I'm very excited to be at this conference and hear that simulations in other natures of dark matter particle scenarios are being ran, so we can actually have something to compare against. And a lot of work needs to get done. And with that, I'll end and say thanks for your attention. Awesome. Thank you.